today we are going to look at solutions. So in the beginning of the semester, we discussed matter. And remember, matter can be broken down into two categories. Matter can either be considered a mixture or a pure substance. So the first 9 weeks we spent talking about compounds and elements and overall properties of pure substances, whereas mixtures, we discussed briefly that it can be broken down based off of what it looks like. So if it is uniform, or if it looks the same, it's going to be considered a homogeneous mixture. And if you can distinguish the different pieces of the mixture, it's considered heterogeneous. Okay, and so some examples of homogeneous mixtures are air, which is a gas and a gas mixture. Sugar and water, this is a solid and liquid mixture. And then stainless steel, remember stainless steel is an alloy, and alloys are solid and solid mixtures. Okay, and so what we're going to do in this unit is we're going to look at homogeneous mixtures. Another word for homogeneous mixture is solutions. Okay, so with solutions, there are two parts. There is a solute and a solvent. So technically, we could write an equation: solute plus solvent equals a solution. So the solute is what is dissolved or being dissolved in a solution. So this is like the salt in salt water, sugar in soda, or carbon dioxide in our soda drinks. Okay, so solutes can be solids, liquids, or gases. And then we have our solvent, which is the medium for dissolving, or what is technically doing the dissolving or the dissociating. So that's water and salt, water and soda. So remember, water is a universal solvent. And so together, if I have salt and water, I get the solution salt water. And so hopefully you remember these terms from middle school. Okay, but with that in mind, when we are looking at something dissolving, okay, not everything can dissolve in any substance. We have to follow the like dissolves like rule, where we have non-polar solutes that dissolve best in non-polar solvents. So it's not saying that they don't dissolve a little bit in a polar solvent, just depending on what we're looking at, but for the maximum dissolving, we're going to have non-polar solvents. Okay, remember covalent compounds, the smaller covalent compounds like hydrocarbons, like CH4, okay, those are considered non-polar. And some examples are fats, steroids, waxes, benzene, hexene, and toluene. Anything that ends in N or E or ane is going to be considered nonpolar. And then, of course, polar dissolves best in polar solvents. So this is our ionic compounds, and it consists of things like organic solids, so like sodium chloride, big sugar, so very complex covalent chains usually have some type of polarity to them. Remember, polarity is an uneven pull on electrons, and so it'll have a slight polarity to it, making it dissolve best in polar solvents. We have water, small alcohols, and acetic acid. So when something is dissolving, we can see dissociation occurring, okay? Or we see something called solvation. And solvation is basically where the surrounding solute with solvent is occurring, or hydration. And that's happening because the solute is more attracted to the solvent than the solute is itself. So that means if I was looking at sodium and chlorine and their bond here, okay, this bond is weaker than their attraction to a water molecule, okay? So instead of sodium and chlorine sticking together because of their weaker attraction than they have with water, they are going to separate and let water surround them. So solvation basically is shown in these two pictures, okay? The positive charge of sodium is going to be surrounded by the partially negative or slightly negative end of oxygen in water, and then the negative chlorine is going to be surrounded by the partially positive end hydrogen within water. And so that is solvation, or what we would call hydration. When we hydrate something, water is surrounding each individual particle within that solution. So with solutes and solvent creating solutions, we look at overall solubility of substances, and there is a trend that relates. So we have something called Henry's Law that talks about how pressure and gas solubility have a direct relationship. We also have other laws or other concepts we look at, but in the end, these are the four main trends that we need to know for this class. One, the solubility of most solids increase with temperature. So I like to think of sweet tea. When you get tea at a restaurant and you pour more sugar into it, normally the sugar is just going to sit at the bottom because the tea is already cold. When you make tea, you have to boil water first and then you pour in sugar, and so that helps increase the solubility of sugar and gives us our sweet tea. The second trend we need to know is the rate at which solids dissolve increase with increasing surface area. So it's like me taking Tylenol or some type of aspirin. So with an aspirin pill, it's going to take so long for it to work. But if I use BC powder that is spread apart or has a greater surface area, it's going to dissolve quicker. So let me show you a visual of this. Alright, so I have an Alka-Seltzer tablet, okay, and we know that we use this for upset stomach. Alright, so when we're looking at increase of surface area, notice how this right here, all of our Alka-Seltzer is packed tightly into this small surface area, whereas if we crushed it up and we kind of spread it apart, it increases the surface area. And so what happens with it dissolving, I'm going to take about 1 milliliter of water, and notice that this is taking a little bit longer to dissolve, whereas this right here will react a little bit faster, and of course they're combining, but you can see right here that this Alka-Seltzer tablet is still taking a while to dissolve, whereas if I look right here, there is no more Alka-Seltzer to dissolve. And so, of course, this shows you that the bigger the surface area, the higher the solubility. This is already dissolved, whereas this is still dissolving. Okay? So that is how surface area increases and solubility increases with it. Let's flip back to your notes. The third trend you're going to look at is the solubility of gases decreases with the increase of temperature. Okay, so I like to think of Coke for this. When you have a Coke, it usually goes flat, or you lose all of your bubbles if you leave it at room temperature because it's warmer. But if you leave your Coke or your soda in the refrigerator, you're going to experience that those bubbles last longer, and that is because the movement of gases slow down, and so they are going to stay submerged within the solvent or the soda itself, and it's going to take a little bit longer to escape. But when you increase the temperature, it increases the molecular movement, and it causes the gas to come out of solution quicker, and so that's why solubility decreases when temperature increases. And then, of course, the solubility of gases increase with the pressure above the solution. So when you have the pressure increasing, it's going to cause a higher movement of kinetic energy in a very small area, and so what's going to happen is those gases are going to be pushed down. So overall, we can see that solids tend to dissolve best when heated, stirred, ground into small particles, and that's just surface area reworded. We didn't talk about this too much, but when something's stirred, it's also known as agitated. Okay, and so when we stir something up, usually it helps increase the movement, increase collisions, and cause things to dissolve quicker. And then, of course, gases tend to dissolve best when the solution is cold and when the pressure is high. Okay, so with this in mind, we can predict the overall solubility trends that we see based off of a solid or gas that we're looking at. And so we are going to look at how these trends occur on something called a solubility chart or solubility curve, where we're looking at how temperature is changing and how that impacts the solubility. So as a reminder, we have saturated, unsaturated, and supersaturated. You've probably heard of saturated and unsaturated in biology. Well, similar to how those prefixes work, we have substances that are considered unsaturated. So if I was looking at everything compared to sodium chloride, and I looked at a dot right underneath here, so at 30 degrees Celsius, 30 grams have dissolved, I would consider that solution to be unsaturated. There's less solute dissolved, which means more can be dissolved. Saturated solutions is where the maximum amount has been dissolved at that temperature, so that is directly on these lines. And then supersaturated means that we have more than the maximum amount at a high temperature, and then it's cooled down. And so we only can achieve supersaturated solutions by heating up the solution and adding more solute to the maximum amount. So real quick, I'm going to explain these terms using a different chart that's less crowded by all of my writing. So let me shift this camera real quick. All right, so we have our solubility chart, okay? And so this is the change in temperature. This is how much water we're dissolving it in, and these are the grams of solute that have been dissolved. There are several different solubility curves here. Do not be afraid of all of this or nervous about all of this, because we're just going to look at one line at a time. And if you have trouble distinguishing between each line at a time, then of course it is best for you to use a highlighter. So I'm going to use a highlighter, and I'm going to give you some examples using potassium chlorate. So first off, if I was looking at 40 degrees Celsius, or a solution at 40 degrees Celsius, and we have, let's say, 10 grams of KClO3 dissolved in 100 grams of water. What I would do is, I know that this whole thing is 100 grams. I would look at 40 degrees Celsius and I would see where it lands on the chart compared to 10 grams. So that's right here. Right? And I could ask you to describe this point. This point would be called unsaturated, or would be considered a unsaturated solution because it falls below potassium chlorate's line. Let's say at the same temperature and the same amount of water, I was looking at maybe 15 grams dissolved. That would fall right here. That would be saturated. Okay, and of course, estimating how much is dissolved will be different for everyone, and so I'll take that into consideration when we're, turning in work. And then lastly, say I kept everything the same, but I said that 30 grams of KClO3 was dissolved. Okay, I would just go to 40 degrees Celsius, go all the way up to 30. I see it's above this line right here, so that is supersaturated. Okay. So that's how you describe as something saturated, unsaturated, or supersaturated. So what we're going to do is we're going to look at different problems that use solubility curves. Okay. So first off, why do solids become more soluble at temperature as temperature increases, but gases become less soluble? Well, we know solids usually have very low kinetic energy, so when we increase temperature, it increases kinetic energy, and then of course it causes more collisions and helps it dissolve better, whereas gases already have a high kinetic energy, so when we increase temperature, it makes them go even faster in it, so it causes them to come out of solution and of course decreases the solubility. So let's look at number 2. Which is more soluble? Solubility is determined by these values here, so whichever one's higher on the chart would have the highest solubility. So I'm looking at NaNO3, and I'm looking at potassium chloride. So I can see NaNO3 is higher, so that means NaNO3 has the highest solubility. And then we get problems like this, where it's not just asking for if it's saturated, unsaturated, or supersaturated. It's asking us for how many grams will actually dissolve. So we kind of do the same process that I showed you earlier. I have 90 degrees Celsius, 100 grams of water, so 100 grams is represented by our graph here. So I just find NH4Cl, or ammonium chloride, and I look at 90 degrees Celsius and I see where it meets the line. That is 70 grams. So in order for my solution to be saturated at 90 degrees Celsius, I need 70 grams of ammonium chloride to dissolve. Okay, so we're considering all saturated solutions, where we want saturated solutions for each of these examples. Well, number 4 also wants to know the grams of ammonium chloride, but at 50 grams of water. All right, so the temperature is still changing. We can't change this chart. So think of it this way. If 70 grams dissolves in 100 grams of water, and this is saturated, how many grams would I need to completely saturate 50 grams of ammonium chloride? Well, hopefully you guys see here that I just divided it by 2. That's my change. So then I would divide this by 2 as well. And I would have 30 grams or 35 grams to dissolve in 50 grams of water to completely saturate the solution. If you don't understand this concept, the best thing is to use the comparison. 70 grams would be considered saturated for this solution. So we want to know what amount would make this saturated in 50 grams. So we just cross multiply 100 grams times x, and then of course this is 3,500 grams. And so then we just divide 100 by each side, and we would still get 35 grams. Okay? So hopefully you can see this is our baseline, this is what the graph reads, and then we divide or multiply by the change of water. So number 5 has that we have KClO3 and 300 grams of water at 30 degrees Celsius. The first thing we have to do is find out how much 30 degrees Celsius is for KClO3 and 100 grams of water. I would say that's about 11. But I am not just working with 100 grams, I'm working with 300 grams. So you can do the relationship, 11 grams in 100 grams of water equals some amount in 300 grams of water. Hopefully you see, oh, I multiplied the denominator by 3, so I'm going to multiply the numerator by 3. I get 33 grams. Okay, so that's how you do that problem. Let's look at a little bit more complex problem. So here in number 8 and 9, it gives us 2 different situations. Okay, I am going to look at number 8 with you, okay? So you start with a saturated solution of NHL at 100 grams of water at 10 degrees Celsius. So let's say ammonia or NH3 at, 10 degrees Celsius is going to be right up here, roughly at 68. Okay? So this value right here is 68 grams. How many grams of NH3 gas would bubble out of the solution if you raise the temperature to 80 degrees Celsius? Well, 80 degrees Celsius is going to fall right here at about 14. Okay, remember these numbers there with the estimation. So depending on how much has bubbled out, we just take 68 and subtract 14 grams. Okay, and when we do that, we get 54 grams have bubbled out. Okay, and number 9, it's the same thing, except we're working with 400 grams of water, so you'll have to multiply your answer by 4 in the end. Okay. But that's how you read the solubility chart. If you remember the trends, you can read this chart with no problem. So our solids always increase in solubility as temperature increases. So anything that has a positive slope is considered a solid or maybe a liquid. Whereas anything that has a negative slope is going to be a gas, and that's just because gases decrease in solubility as temperature increases. So hopefully the charts make just a little bit more sense for you. Alright, so then let's look at electrolytes and non-electrolytes. Electrolytes, remember, is basically an ionic compound that has been dissolved or that is in solution. And so electrolytes are a substance that we consider an aqueous solution or in a solution, and it conducts an electric current. So you may think as soon as you hear electrolytes, Gatorade. All right, athletes drink Gatorade to restore their electrolytes in their body to help with the electric currents that help move our muscles in our body. And we have non-electrolytes. These are substances whose aqueous solution does not conduct an electric current. So I have listed some examples here, and these are the only examples I'll ever give you on any assignment, just because the complexity of this can be pretty difficult, and so I'm just going to keep it very simple and save the rest for AP chemistry or organic chemistry. But first off, we have a pure water, and we know that doesn't conduct electricity, so that's not a non-electrolyte. Tap water and sugar solutions are non-electrolytes. Ethyl alcohol solution, the way that it is bonded together, so we have an OH here, and so that oxygen, of course, is going to change its polarity slightly, so it's going to make it a very weak electrolyte. We have sodium chloride, of course, which is going to be an electrolyte because it is a ionic compound within a solution. Lactic acid we consider an electrolyte, and that's just because of the oxygen that's changing its polarity. Hydrochloric acid is an electrolyte, and then pure sodium chloride, so just salt, is considered a non-electrolyte. For a ionic compound to be an electrolyte, it must be submerged in a solvent, right? So now we've looked at properties that don't really depend on concentration, like pressure and temperature and volume, of course. We haven't really looked at how the amount is impacting those properties. So what we're going to do is we're going to now look at colligative properties, properties that depend on the concentration of the particles. So this just means the number of solutes or solute particles within the solution, and it does not depend on the identity of the particles. So three main properties we're going to look at: boiling point elevation, freezing point depression, and osmotic pressure. I won't go too far into osmotic pressure because that's what you learned in biology, or the amount of additional pressure caused by water molecules that move into a concentrated solution through a membrane, so like biological systems such as the uptake of nutrients. So we hopefully you remember hypertonic, isotonic, hypotonic in biology. That's what osmotic pressure is, and it's all about the concentration or the amount of solute within that solution. What we are going to look at in more detail is the freezing point depression and boiling point elevation. In a solution, the solute particles interfere with the attractive forces among the solvent particles. This prevents the solvent from entering the solid state at its normal freezing point. So this is why we salt roads in winter. Okay, so what happens is we have water on the roads after a rain, and the temperatures are going to go to freezing or below freezing. So the government or our county is going to add salt to the roads, and what happens is we're adding more solute to the water on the roads. So it has a higher concentration in that water. And so because now the water has solutes, these solutes are going to prevent the water from freezing or coming together as easily, and so it's going to decrease the freezing point, and that way water doesn't freeze at, say, 0 degrees Celsius. It's going to decrease at maybe negative 20 degrees Celsius. So it helps prevent ice from forming on the roads. Then we have boiling point elevation, and this is when a solution contains non-volatile solutes. Additional kinetic energy is needed so that way our vapor pressure and atmospheric pressure can come together, and then the greater the number of solute particles in the solution, the higher the boiling point elevation. We always like to use the example salt in boiling water. Okay, so when you cook spaghetti, you usually add salt to the water, and what happens is it increases the temperature for the boiling point. So what happens is we're cooking the noodles at a higher temperature, and it increases the overall cooking quality, or I guess you would say it would decrease the time it takes to cook it. Okay, and that is boiling point elevation. We're raising the boiling point by adding solute to it. Okay, so then we get into our overall math of this unit. So solutions, remember, is how much solute is dissolved in the solvent. So when we say something is concentrated, there's usually a large amount of solute. So like sweet tea, if it's very sweet, it's a high concentration sweet tea, or a high level of salt within that sweet tea. If we say, oh, this tea is diluted or has a low concentration, that usually means there's a small amount of solute. And so when we use concentration, we are looking at it quantitatively, not qualitatively, as we have looked at before. And excuse my vocabulary, my English here, I am struggling today. But basically, concentration is the quantitative values. We use molarity, percent mass, and molality to describe how much solute is within a solution and its overall concentration. So let's look at these terms, okay? So when we are looking at calculations of solution concentration, we look at percent by mass or percent by volume. Basically, we are doing a part over whole calculation, okay? So if I want to know the concentration of a solution, so if I ask for percent concentration, this means we want to know how much solute is present. If I ask for percent water, that's how much solvent, because remember, it is the medium. Okay, so this could either be mass of solute or mass of solvent. So in the end, if we're asking for this, we would say it's solute divided by solution times 100. If we're asking for water, we would do solvent divided by solution times 100. So in this example right here, it says, in order to maintain a sodium chloride concentration similar to ocean water, an aquarium must contain 3.6 grams of NaCl. This is our solute per 100 grams of water. This is our solvent. What is the percent by mass of sodium chloride? So it wants to know the percent of solute in the solution. So we're going to use this equation. Solute over solution times 100. Well, I have the solute, 3.6, but I do not have the solution. Well, remember what I said earlier, that we can do solute plus solvent to give us the solution value. And that's because if I'm looking at salt water, it's going to be made up of salt and it's going to be made up of water. Well, I have the salt and I have the amount of salt water, so I'm just going to move the equation around, or I have the salt, sorry, and I have the water. Now I just need to find out how much it is when we put it together. Well, we know mass cannot be created or destroyed, so I'm going to take 3.6 for the solute, add it to 100 grams for the solvent, and it's going to give me 103.6 for my solution. So now I have my solute over solution, multiply it by 100, and I get 3.5%. Okay? The same thing is going to go for percent by volume. Okay, if they give us milliliters and milliliters, milliliters of solution, milliliters of solute, then I'm just going to put volume over volume. As long as you remember solute over solution, or if they're asking for the solvent, solvent over solution times 100, you will be good to go. Another thing is what happens if they don't give you grams of water. So let's just say I took this, and instead of giving you 100 grams, I gave you 100 milliliters of water. All right, well, that's mixing grams and milliliters. And if I divided the two, that would give me density. And I can't add up milliliters and grams to give me the solution. Well, what this all means is that we're going to have to change milliliters of water to grams of water using its density. So the great thing about water is water has a density of 1.00 grams per milliliter. Okay, so it's a 1-to-1 ratio. Right? If I have 100 milliliters of water, it's actually 100 grams of water. And so when water is given to you in milliliters, you can change it to grams if your solute is measured in grams, or if it's given to you in grams and you need milliliters, you can switch it back to milliliters. And I'll show you some examples of that in my next video. Alright, so let's look at the next quantitative description. We have molarity, and this is the ratio of moles of solute to liters of solution, okay? And so basically when we ask for concentration or we ask for molarity, it's the same thing. And the units we use for this have been described up top. It's either a capital M or moles per liter. Okay, and so the molarity is taking the moles of the solute and dividing it by the liters of the solution. So the example in your notes says, calculate the molarity of 1.60 liters of solution containing 1.55 grams of dissolved KBr. Well, this tells me if it's being dissolved, that's our solute. So I'm going to take 1.55 grams and change it to moles. Okay, and you just know this is the molar mass from the periodic table, and we get 0.0130 moles. And then we're going to take moles of our solute, divide it by the liters of solution they gave us, and we get 0.00813, and then this is the molar concentration. So you could say moles per liter, or you can put a capital M for molarity. Alright, so that is molarity in a nutshell, and we'll do some examples of that in our next video. Just notice that we're comparing or looking at the ratio of moles for liters of the solution here. And then lastly, when we are looking at molarity, we can make dilutions, okay? And so with this in mind, because mole amount does not change, we can replace, our volume, or not our volume, we can change this amount right here to molarity, okay? And so basically what this all means is when we have a concentration, okay, we're looking for molarity, and it's always moles divided by liters, okay, and this is considered our volume. Well, if moles are not changing, that's a constant, so I can move everything that's not a constant to the other side. So volume is not a constant, so I'm going to multiply each side by volume, and I get volume times the concentration equals the amount, okay? So if I'm not changing the amount, but I am changing the volume, okay, I can have an initial situation or an initial volume where molarity changes, and then I can have a final volume, which changes the concentration. So in the end, I get M1B1 equals M2B2. That is what dilutions are. It's looking at an initial concentration and volume, and then it's seeing how the molarity changes once I add more water or once the volume changes. Okay. So an example of this would be, what volume in milliliters of 2 molar concentration calcium chloride stock solution would you use to make 0.50 liters of 0.300 molar solution of calcium chloride? So first off, stock solution just means that there is a concentrated solution of standard molarities, okay? And so what we do is, if we're making this, this is going to be our M2 and our V2, so right here, okay? And you can either keep it in liters or you can change it to 2 milliliters already. The great thing is what you have on one side will be okay as long as it's the same on the other side. It doesn't have to be liters right here. It does not have to be milliliters. But they gave us liters, so I have 0.5 liters here. Okay, the end is asking you for milliliters, so we're just going to move the decimal place 1, 2, 3 to the right and actually get 500 milliliters. So we're looking for the initial volume when the concentration was 2.00. So we're just going to plug that into our equation. I have M1 times V1 equals M2 times V2. And when we move the equation around, we get 75 milliliters. So that means we created a solution. So as we do labs, I make certain solutions based off of whatever concentration that we need, okay? So this is considered a volumetric flask, okay? And say that this right here is 75 milliliters, okay? And so it has a concentration of 2 moles per liter, okay? So then what happens is I take only a certain amount of this, or I take this and I put it in a larger container, and this container is going to be 500 milliliters. Okay, so what happens is I take my 75 milliliters and I pour it in here, and so it fills up to maybe like right here, and then I add water to fill up the entire volumetric flask. When I add all of that water to it, what happens is the concentration is going to decrease from 2 moles per liter to 0.3 moles per liter, and that's because we've decreased the amount of solute compared to the amount of solvent, or how much of the solution there is. So remember, we're comparing the total concentration of solute. So that's like saying that you have some dye. So let me actually get something out for you guys. So here is some dye. So we'll say this is the solute, or the concentration, or this. We would say that's the solute, okay? So notice this is a milliliter, 1 milliliter of water, okay? And we have a set amount of dye, or a set amount of calcium chloride in this example, okay? So it has a certain concentration, and we can tell it has a certain concentration because of the color. Well, what happens in a dilution when we dilute something? It's like diluting tea. You add more water to it and it makes it less sugary. So what I'm going to do is I'm going to increase the volume to 4 milliliters, and notice what happened to the concentration of this dye. It is significantly lighter, okay, and I know like the shadows of course kind of throw it off, but if you look at this, it is not as dark as it was starting off, and that's what dilutions is, okay? It's increasing the amount of solvent compared to the solute, and it's decreasing the concentration. So we'll look at more examples, mathematical examples of all of these in our next video, and then what we'll do is we'll talk about how dilutions are made in a third video.